Welcome back to linear algebra. In this video, I want to talk about vector space isomorphisms. The word isomorphism is probably something that you're not very familiar with, but the concept is fairly straightforward at a surface level. In mathematics, we use the word isomorphism to describe a situation where two structures can, in some way or shape, be interchanged with each other. A more visceral example than the things we're going to be looking at in today's lesson comes from the branch of mathematics called graph theory. Graph theory deals with analyzing the connections between different objects. Think about it in terms of, say, a subway map or a map of bus routes. If you have a couple of stops, let's name them as A, B, C, D, E, F, and G. I drifted over a little bit too far, so I'm in my own way. Let me move that where you can see all of it. That's better. So we have a bunch of bus stops or a bunch of stops on a subway route, and we can look at which of these are actually linked up. Let's say that A goes to C, D, and E, B goes to C, D, and E, C and D go to F, D and E can go to G. So you have a bunch of different routes here. One interesting thing that we can do, the London subway map famously is an example of this. This map is kind of confusing. It's a bit of a mess because you have all these routes that are crossing over each other. It makes sense at first glance to lay out bus routes in terms of the geography of the region and where the buses or subways are going. But if we rearranged these points in a very careful manner, let's put C, D, and E right across the middle like this. Let's put F and G really close to those. And let's put A and B really far away. Now A maps to C, D, and E. I'm sorry, I drew that backwards. I said A, I drew it for B. But it's also true that B maps to C, D, and E. So we've got A and B, which both map to C, D, and E. None of C, D, or E map to each other, but C and D both map to F, and D and E both map to G. So by rearranging the figure like this, we can lose the physical space connection, but make it a lot easier to understand how these things are connected to each other or where the connections are. Again, graph theory itself, not something we want to talk about in this course, but thinking about the fact that there's a sense in which these graphs are the same thing, they're conveying the same information, I think will help you understand what we're talking about when we get into vector space isomorphisms. So at that, let me get my head out of the way. Let's scroll all of this off of the screen and start looking. Let's let V and W be two vector spaces. We will say that V is isomorphic to W if and only if there is a one-to-one and onto linear transformation T that maps from V to W. If V and W are the same vector space, we almost never talk about an isomorphism there, although technically speaking, it can exist. And actually, it's something that we've already worked on in this course. We just don't call it an isomorphism. If V and W are different vector spaces, that's where this starts to become interesting. A one-to-one and onto linear transformation from one vector space to another can be called an isomorphism between those vector spaces. And we'll say that V is isomorphic to W. A very simple theorem, but technically something that needs to be proven. If you have an isomorphism T that maps from vector space V to vector space W, well, an isomorphism is both one-to-one and onto, so the inverse exists. And we proved previously that the inverse is one-to-one and onto, so we have an isomorphism from W back to V. And not only is V isomorphic to W, but W is isomorphic to V as well. All right, that's all well and good. Getting a little bit ahead of myself. I don't want to put my theorem down just yet. So let me scroll back up just for a moment. When we're talking about an isomorphism, because linear transformations preserve linear combinations, you can think about an isomorphism as a way to take a linear combination in one vector space and calculate it in a different vector space. That's going to be the first of several different things that we do with an isomorphism. The applications of isomorphisms are going to wait just a little bit. Understanding a little bit more about the structure of isomorphism is going to help us get there. All right. Our book doesn't call this as such. And in fact, there's a different thing that takes this name, but I tend to think of this as the fundamental theorem of linear algebra. This is the reason that linear algebra is so useful and why we spent so much time dealing with Euclidean vectors, even though we want vectors to mean such an arbitrary abstract thing. Let V be an n-dimensional vector space. Then there is an isomorphism between V and Rn. Every vector space is isomorphic to a Euclidean vector space. And I love the proof of this theorem because it's very constructional. Let's find a basis for vector space. I forgot the words. Let's define a basis for vector space V. Since we said that V is n-dimensional, that means its basis has n vectors in it. We'll call them u1 through to un. And a linear transformation is fully defined by its action on a basis. So in order to define a linear transformation from V to Rn, we can simply pick ways of evaluating our transformation on each of these basis vectors. The natural transformation, we'll call this, takes each of those basis vectors and turns it into a Euclidean unit vector, E1, which is 1, 0, 0, down through all the zeros, 0, 1, 0, lots more zeros, all the way down to 0, 0, lots of zeros, ends in 1. Certainly, this is a linear transformation. We can define it to be a linear transformation. We need to show that it is an isomorphism. To be an isomorphism, you need to be one-to-one and onto. Right. To show that a transformation is one-to-one, we always take two vectors out of the domain so that when we evaluate the transformation on each of those vectors, we get the same thing. So pick v1 and v2 in vector space V, such that t of v1 is equal to t of v2. Now, we don't know a lot about vector space V. All we know is we have one basis. Since B is a basis for V, remember, every vector in a vector space can be written as a linear combination of the basis vectors. So we can write V1 as, let's call it A, A1 U1 plus A2 U2 plus ... plus AN UN. So with that, T of V1 is going to be A1 times T of U1 plus A2 times T of U2 . I'm skipping the step where I substitute that in because this is going to take a lot of writing as it is. But you can use the linearity to split up your linear transformation over the linear combination. And you can use the definition of the linear transformation to rewrite that thing as a combination of the Euclidean unit vectors. And we know, as we've seen many times, a linear combination of the Euclidean unit vectors is a vector that has the coefficients as its components. I'm not going to go through and write everything out again. But similarly, because we have a basis, we can find the linear combination b1u1 plus b2u2 all the way down to bn which is a representation of vector v2, and we can evaluate our linear transformation t on v2. We can go through the whole process, and I encourage you to do so if you would so desire, but I'm going to jump right to the conclusion that this gives us the Euclidean vector with components b1, b2 down to bn. Now, why is that useful? Well, that's useful because we assumed that t of v1 was equal to t of v2. Which means that the Euclidean vector a1, a2 down to an is equal to the Euclidean vector b1, b2 down to bn. And two Euclidean vectors can only be equal to each other if their components are equal to each other. And that's useful because if I take v1 and I write it once again as the linear combination, I can substitute in and replace a1 with b1 because they're equal. And because I can do that, this linear combination is exactly defined as the representation of v2. So, fairly long way to go to get there, but we've seen now that we have a one-to-one linear transformation. The other claim is that T is onto. In order to show that something is onto, you start off by taking something out of the codomain. In this case, our codomain is Rn. So we'll call this vector W, but we know what a vector in Rn looks like. It's a column vector with n entries. I'll call them C1, C2, down through to Cn. And so I need to find a match I'll call little v. And let's take the linear combination C1U1 plus C2U2 plus CNUN. Since these U vectors are a basis for vector space V, this linear combination is in vector space V. And I'm not going to go through the whole process one more time. We've seen it a couple of times already. But you can go through and use the definition of the transformation the same way we did in the previous portion to get from T of V1 down to W. And that's what it takes to be onto. We started with a linear transformation. We showed that it was one-to-one. We showed that it was onto. Therefore, this linear transformation is an isomorphism. Now that we've got that, how about a corollary? it turns out that all we need is to have two vector spaces of the same dimension in order for them to be isomorphic. You can make this statement more powerful. If you have vector spaces of the same dimension, then they are isomorphic. If you have isomorphic vector spaces, then they have the same dimension. I'm not going to prove the second part in this video just because we're running low on time, but I think this is an interesting corollary that doesn't take that much effort. From our main theorem, because V and W are both n-dimensional vector spaces, then there are isomorphisms from either of those to Rn. And because an isomorphism is one-to-one and onto, then they have inverses. So we can take S inverse which is also an isomorphism. So also one-to-one and onto. I'm kind of running low on variables here. Let's call it Q. Q doesn't get used all that often. And I claim that if I compose S inverse with T, I will also have an isomorphism. In order to show that, I need to show that Q is linear, is one-to-one, and is onto. Right? Well, to show something is linear, we evaluate it on a linear combination. And because Q is a composition, this is S inverse of T of C1V1 plus C2V2. T is an isomorphism, so it's a linear transformation. And S inverse is an isomorphism, so it's a linear transformation. And hey, we have composition again. So Q of C1V1 plus C2V2 is the same thing as C1 times Q of V1 plus C2 times Q of V2. Well, if Q of V1 is equal to Q of V2, then that's the same thing as saying that S inverse of T of V1 is equal to S inverse of T of V2. And since S inverse is an isomorphism, it's one-to-one. So S of one vector is equal to S inverse of the other vector if and only if those vectors themselves are equal, because S inverse is 1 to 1. Likewise, T is 1 to 1. So T of V1 is equal to T of V2 if and only if V1 is equal to V2. And then finally, onto. Take vector W in W. And notice that if we take T inverse of S of W, and we name that V, that's something in V. And again, because T is an isomorphism, it's 1 to 1 and onto. And if it's 1 to 1 and onto, it has an inverse. We already established that S inverse has an inverse, which is S. So T inverse of S of W, call that thing V. And Q of V is equal to S inverse of T of V, but then replacing V, this is the same thing as S inverse of T inverse of S of W. And T of T inverse of a thing is going to be that thing. And S inverse of S of W is going to be that thing. So this function Q not only is a linear transformation, but it's also 1 to 1 and onto. And that's what it takes to be an isomorphism. As I said, for the sake of time, I'm not going to go through the proof that given two vector spaces which are isomorphic, that the vector spaces have the same dimension, but that is also the case. If two vector spaces have the same dimension, they are isomorphic. If two vector spaces have different dimensions, they are not isomorphic. An interesting, useful result that we just don't have time for in this video. So I'm going to wrap up here. And in the next video, I will show you how we can use isomorphisms to make any kind of linear transformation a matrix transformation, which is really the whole point of this entire course.